I got my bachelor's degree at a nice little college down in West Virginia called Davis College many years ago, 1933 as a matter of fact, in the very depths of the Depression. Got a job with DuPont, fortunately, in 1933, and I worked there for a couple of years in the control laboratory at Bell, West Virginia. And I didn't like the work too much because it wasn't very creative. And I wanted to do something better, so I had the opportunity to go back to school. A friend of mine, by the name of Henry Rutherford, was already at George Washington University, and he persuaded the head of the department there to offer me a fellowship, which he did, and I accepted. And that's 1935. So I went to George Washington University to start out my graduate work, and at that year, a very famous chemist by the name of Paul Emmett was giving a course in kinetics and catalysis, and the head of the department told me, "You must take Paul Emmett's course," which I did, and that's when I first became really interested in the field of catalysis. Paul Emmett's course was a very enjoyable course. It was taken by practically all the chemistry graduate students in those days. He gave the course every other year. He, at that time, was located at the fixed nitrogen laboratories of the Department of Agriculture, and he was an adjunct professor at the university. And at the end of the first semester of his course, I went up to Professor Emmett and I said, "Professor, would you consider being my advisor on my master's thesis?" He said, "Well, Roland, I don't know." I think he's called me Mr. Hansford at that time. He said, "I'm only an adjunct professor, and I'm not sure that they'll allow me to do this. I'll let you know." And the next lecture, he called me up and says, "I'll take it." And he offered me the choice of 3 different subjects. And I chose one, which was the hydrogenation of ethylene on the famous synthetic ammonia catalyst that had been developed at the fixed nitrogen laboratories some years before. And I started to work on the thesis that year, 1935, late 35. I built my apparatus, which was similar to a conventional BET apparatus, but not quite the same. And then in the fall of 36, I started to actually make my measurements in the hydrogenation of ethylene over pure iron synthetic ammonia catalyst, unpromoted. This catalyst, by the way, is not used in the synthesis of ammonia because it's not too stable, but that's where we started. And I started to work at room temperature, I mixed up hydrogen and ethylene, put it on the catalyst at room temperature, and took my measurements, and it looked like very funny. I took the first data out to Paul Emmett. He required that I come out to see him. He wasn't at the university that year. And he said, "There's something wrong here." So it looks to me like the reaction is all over before you start taking measurements. And sure enough, that's what happened. I lowered the temperature to ice temperature, and there was still some reaction available at the end of the time that I admitted the gas mixture to the catalyst. So this gave us a clue that the temperature was still too high. And Paul said, "Well, take it down to dry ice temperature, because I don't think anything's going to happen there." Because that was the region in which a type A hydrogen absorption had been observed by Burt and Emmett, and has never been observed before to enter into a chemical reaction. So I took the temperature down to dry ice temperature, -78, and it was a nice, steady reaction. I almost caught all of it before I made my first measurements. And then Emmett said, well, let's see if we can go lower. And so I used the old-fashioned technique of bubbling air through a acetone dry ice mixture, and I got down to -89. And the reaction was real nice at that temperature, very easily measurable, but it was still rapid enough, and I was able to capture practically the whole reaction. And Emmett was excited about this because this meant that type A hydrogen absorption was activated absorption of some kind, and it was actually entering into the reaction. So we studied the reaction over many different ratios of hydrogen to ethylene to determine the order of the reaction and so on. And then Professor Emmett said, well, now you've studied pure iron, let's see what happens to promoted iron catalyst, which, if you remember, the promoted iron catalyst of commerce really contains about 1% alumina and 1% or so of potassium. And Brunner and Emmett had already determined that the promoters covered something like 80% of the surface area of the catalyst. And incidentally, I measured the surface area of my catalyst by the old technique that was developed by Brunner and Emmett, namely the point A method. The Brunner-Emmett Teller theory had not been developed at that time, and so I had to use the type A method where the isotherm bends and then extrapolate back to zero. And I came up with numbers which were consistent with what Emmett and Brunner had found, namely around 8 or 10 square meters per gram on the pure iron catalyst. And then we did the same thing with the promoted catalyst, and we found with promoted catalyst the reaction was extremely slow. This was really amazing. But we couldn't quite understand this, and we didn't understand it until years later, when Emmett, after Emmett had gone to Hopkins, he had one of his graduate students there to repeat my work, and with propylene and ethylene as well. And he found that with propylene, the promoted catalysts were quite active. So this suggested some kind of a steric effect on the surface. I don't think we ever came to a firm conclusion about the mechanism, but anyhow, that's what the results were. The iron synthetic promoted catalyst was very active. The promoted catalyst was not so active. I'd say an order of magnitude less active than the promoted catalyst, which is a very interesting observation. Well, at that point, Professor Emmett went to Johns Hopkins. That was in 1938, or late 37 actually, and I had finished my study on the two catalysts with ethylene, and that was my master's thesis. And I had to get back to work because I had some family obligations and some debts left over from my undergraduate days, so I was not willing to go to Hopkins with Emmett because he told me, he was the head of the chemical engineering department, and therefore I would have to go back and take all the undergraduate courses in chemical engineering, and it would take me another 5 years. Well, 5 years at that time seemed like a long time to me, so I said, well, I'll get a job, then I'll work for a few years, and I'll come back. Well, you know what happened? I didn't come back because the war came on, and I stayed on the job. I got the job, by the way, at Saucony Vacuum Oil Company. In those days, it was now known as Mobil Oil Company, in Paulsboro, New Jersey. And during the war, I worked on catalytic cracking and also on these production of butadiene for synthetic rubber, and we developed a process for that, but it never became commercialized. It turned out it was a reaction with sulfur, between sulfur and normal butane, and half the product was thiophene. the other half was butadiene. And it seemed like an interesting question to recycle the butadiene to make more, practically 100%, well, not theoretically, but around 100% thiophene, and there was an interest in thiophene for a while, but it never really panned out to be a commercial product. But anyhow, we succeeded in making butadiene, but the Huger process with, I guess it was chromium catalyst, and the adiabatic process developed by the Huger people was the one that was used for the production of butadiene from butane. So, Burt, I think well, as I mentioned, I worked on in the field of catalytic cracking during the war, and Dr. Milton Marisic, early in the war, about it was 1943 or 44, had invented a new form of cracking catalyst called by the mobile people bead catalyst. And Marisic left the company about that time to go to Pure Oil Company, and I took over his group. And in the group, there were some well-known chemists today. Charlie Plank is one of them, and Leonard Drake, and also Dr. Ritter were in the group. And we worked, some of us, Charlie and I particularly, were working on cracking catalysts and the structure of cracking catalysts. And it had been observed before by one of Marisic's helpers, Ed Geist, by name, who left the company too sometime later and went to Corning Glass. But Ed observed that when they put methyl red solution on the bead cracking catalyst, it turned red, which means that it was acidic. But that's about as far as that went. But later, Professor Walling and my friend Hans Bendisi came out with much more extensive indicator studies of cracking catalysts and proved that they were really strong acids. And so we worked on this problem to try to come up with a mechanism. And of course, it's quite obvious if you have a strong acid that one of the most likely things to happen is that you make carbonium ions, like sulfuric acid or other strong acids. And it turned out that the cracking catalyst really had centers that were strongest, 90% or 90% plus sulfuric acid. But in no way would they be considered as super acids, as we know some of the, like HF, animal pentafluoride and so on, because they would not catalyze the isomerization of normal butane without some dehydrogenation component. But anyhow, it looked as though the carbonium ion mechanism could apply. Now, we were not really the first to suggest this. I think Charlie Thomas at UOP and later Greensfelder at Shell came up with a much more comprehensive study of this question of the mechanism. And actually Greensfelder came out with some very nice correlations showing that the mechanism did follow a carbonium ion reaction. I want to say that I think we were the first, though, to show that if you put deuterium oxide on the surface of the catalyst and then studied the interchange with the hydrocarbons, such as normal isobutane and other hydrocarbons, we just studied a whole number of hydrocarbons, they become an exchange reaction. And in the case of isobutane particularly, it was only the primary hydrogens that exchanged. The tertiary hydrogen did not exchange, which was exact proof that there was a carbonium ion mechanism. I think we were the first to show that. And then the carbonium ion mechanism became widely accepted among petroleum chemists as the mechanism for catalytic cracking. We know that the fragments are largely iso compounds, both saturated and unsaturated, you get hydrogen transfer reactions, which are typical carbon-amine reactions. So at that point, I left Mobile. It was still Seconic Vacuum when I left to go to Union Oil Company in California. I wanted to live in California, and there are other reasons why I didn't want to stay at Seconic Vacuum. Anyhow, I took the information or my background in catalytic cracking and transferred it to hydrocracking, which would not be a conflict with what I've already done at Seconic. So I was able to carry this expertise, if you want to call it, over to hydrocracking, and we were quite successful there at Union. We developed a process which is known in the industry today as unicracking, but it's based on an entirely different catalyst than what we had been used to, namely the zeolite catalyst, Y-zeolite primarily, which is, of course, used today also and before our time in catalytic cracking. But we were the first, I think, to apply it to hydrocracking. And it was a very successful process, and it's still in use in the industry.
How did you get involved in the infrared?
Infrared?
Yes, the infrared work with John Ward.
Well, with John Ward, John came to it's now called Unical. At that time it was Union Oil Company in California. John came around, I guess it was around 25 years ago, from England. Or actually, he came from Canada, but he had received his education at Oxford, at Cambridge. And John was an infrared expert, and he set up an infrared apparatus and studied the absorption of hydrocarbons, primarily on cracking catalysts and on zeolites, amorphous and crystalline cracking catalysts, and he was able to demonstrate almost directly that there was a carbon-amine formation between the surface of the catalyst and the hydrocarbon. I didn't have too much directly to do that. John was the expert, but he and I collaborated on a couple of papers. I've forgotten now what they were. It had to do with the cracking of what was it? This is so many years ago, I've forgotten. It had to do with a reaction involving the transfer of methyl groups, like isomerization of orthoxylene. I think that was the reaction.
Yes, the xylene isomerization.
Yes, xylene isomerization. And this turned out to be a very useful tool in conjunction with the infrared work. It was pretty well demonstrated that true enough there were carbon-ion mechanism involved in the isomerization. So we published a couple of papers on it, and I've forgotten the exact details, but after all, I've been retired for 12 years, so and that was 20 years ago. And I don't remember the details. Now, Burt, do you have any?
Now, you had a story about Sir Hugh Taylor and Paul Emmett.
Oh, yes, well, that's a little sort of a human side. I went to Davis Hawkins College in 1929, and shortly, a few years just before, I think it was 25 or 26, a young professor came over from the University of Virginia to head the chemistry department at Davis Hawkins. And he had received his training in catalysis, really, although he didn't really excite me about catalysis at the time, but he had received his training under Arthur Benton at the University of Virginia, and also Robert Pease. But at the same time, Benton took a leave of absence sabbatical, I suppose you'd call it, and went to Caltech. And at Caltech, Arthur Benton became Paul Emmett's thesis advisor, and Emmett got his degree under Arthur Benton. And so did my professor at Davis Hawkins, my undergraduate professor, he got his degree under Benton. And it so happens that Arthur Benton was a student of the, I guess he would call him the pioneer catalytic chemist in this country. His name was Sir Hugh Taylor. He wasn't Sir at that time, but it was Hugh Taylor at Princeton. And so it turned out that here I am a student of Paul Emmett, and Emmett is a student of Arthur Benton, and Arthur Benton was a student of Hugh Taylor. Therefore, that makes me catalytically the great-grandson of Sir Hugh Taylor on two sides. My undergraduate professor, who had a great influence on my career, really. He gave me Purdom, his name was Raymond Purdom. He gave me individual instructions. Really, there weren't many people majoring in chemistry at that time. And so he took me under his wing and gave me private instruction, even in the physical chemistry course, which I was the only student in the course. And Dr. Purdom trained me personally in this area so that I got a darn good education as an undergraduate. And when I went to George Washington 2 years later, I graduated in 33, and 35 I went to GTEC because I spent 2 years, as I mentioned, with DuPont. And then Dr. Emmett, who was really quite a young man at that time, he was only 35 years old, you know, he inspired me to get into catalysis. So really, that's how I got into the field.
Now you recalled only one time that you ever saw Paul Emmett get upset or angry.
Well, that happened at a meeting in Washington. I think it was a local chemical society meeting, and Sir Hugh Taylor was there, and Arthur Benton was there, and Paul Emmett, and among many others, of course. And I don't recall the exact subject matter, but anyhow, it's the only time I ever saw Paul really lose his temper. Taylor, you know, those of you who know him or knew him, was inclined to be a sort of a bull-headed Englishman, so to speak. And he had really firm opinions about things. And he disagreed with Emmett, and I think it had to do with Benton's stepwise absorption, as I remember. And he disagreed with Benton, and he disagreed with Emmett. And they got into a discussion, and I remember Paul said to him, finally, he says, "Well, Professor Taylor, if you weren't so damn bullheaded, you'd understand this." Words to that effect. Anyhow, that's the only time I ever heard Paul use the word damn, I think. And I knew Paul a good many years. That's the incident that I referred to. That goes back to 1936, I think it was, thereabouts. So that's a long time, too.
Now, how would you describe Paul Emmett?
Well, Paul was a taskmaster, first of all. He had to be sure that everything was exactly right. I think I've told Burt before about the story that when I finished my bachelor's thesis under Paul, and I'd already gone into industry with secondary vacuum, and Paul was going over the data from my thesis and getting ready to make a publication of paper. And he had read someplace that nickel catalyst, metallic nickel, would cause the polymerization of ethylene. And this worried him. He said, well, now, iron isn't too far different from nickel, so suppose what Roland found there was a polymerization reaction instead of a hydrogenation reaction. Because we were studying the reaction with a constant volume system and studying the pressure change. And despite the fact that I demonstrated that the pressure drop was exactly what we predict on the ratio of hydrogen to ethylene in the system, Paul was not satisfied. He said, well, maybe you're getting polymerization. And I was up in Paulsboro at the time. He said, I want you to go back down to the university, and my apparatus was still intact, and make another experiment and analyze the product to make sure that you did not get polymerization. In other words, the polymerization would involve the formation of butylene from two molecules of ethylene instead of ethane from a molecule of hydrogen and ethylene. So at that time, we didn't have gas chromatography, we didn't have mass spec, anything like that. The best thing we had was an old Orsat type of analysis. And the analysis to differentiate between ethylene and butylene was only a matter of using a different strength of sulfuric acid. With ethylene, you required very strong sulfuric acid, 98% or 96%. And if you use 90% sulfuric acid with a silver sulfate catalyst, or saturated with silver nitrate, silver sulfate, then you pick up only butylene. So I made up such an apparatus and trudged over to Philadelphia and got on the Pennsylvania Railroad. In those days I didn't have a car, and I went down to Philadelphia, to Washington from Philadelphia with my little Orsat apparatus on the train. I guess everybody thought I was nuts. With a peculiar-looking piece of apparatus as it was, but it didn't bother me. I went down to Washington, went back to the lab. I don't remember where I stayed. That's what I've been thinking a long time about that. Where the heck did I stay? I must have stayed with my friend down there, Henry Rutherford. I can't remember. Anyhow, I went over to the lab. I made another experiment. I used a 1-to-1 ratio of hydrogen to ethylene. And this was dry ice temperature. It went according to Hoyle. Everything, the reaction seemed to be complete. And I collected the product into the Orsat apparatus and to see if there's any absorption of gas in 90% sulfuric acid saturated with silver sulfate. There wasn't a bit. It was perfect. So this demonstrated that there was no butylene produced, so that eliminated the polymerization theory. But that shows you how really precise and what should I say, the right word, he had to be sure, absolutely certain, that the results are what they said they were. And so he was satisfied when I reported that there was no absorption, and it was truly a hydrogenation reaction. And it turned out, of course, that the kinetics said the same thing. So that shows you how meticulous Paul Embry was in his research. And that's characteristic of everything he did, even at the fixed nitrogen laboratories, and years later, he required his graduate students to be just as meticulous.
Now, what kind of a teacher was he?
Well, Paul was an excellent teacher, but you had to be on your toes to keep up with him. I remember his lecture, particularly in kinetics. He used the blackboard an awful lot, but he used the eraser just about as fast as you put the stuff up. And if you didn't get it down in your notebook, it's just too bad. But he was an excellent teacher, really. And particularly if you worked with him directly, like I did when I went out to the fixed nitrogen laboratories to discuss our results. I recall at the end of that kinetics course, it was a tough course, but very interesting. He gave an open book exam, and you could bring anything you wanted to take the exam. And he had this list of questions. I wish I had a copy of those questions, but I don't. Anyhow, I struggled through it with a lot of effort, and I wasn't sure that I didn't want to pass the course. And it was such a tough exam. And it turned out, he graded the exam on the basis that if you understood what the question asked, you got full credit for it. And I did. I passed. I'm sure I didn't understand all the questions that were asked, but anyhow, I understood that and I passed the course. But he was a good teacher.
Well, now you told us a story about the erasers and the blackboard at the Gordon Conference.
Well, that's a different battle of the erasers, they called that. That was between Paul Weiss and Tom Gray. This was at the Gordon Conference, I guess around 1955, someplace in that range of time. Paul Weiss was at Mobile at the time, and he was a proponent of the semiconductor theory, even to the extent of trying to make amorphous silicon aluminum a semiconductor, which is ridiculous, really. And that was what the argument was about, I think, as I remember. And Gray, while Gray was also a proponent of the semiconductor theory in catalysis, having published some papers on this area, I don't think he published it with Dowden, who was one of the pioneers in this area, but anyhow, Gray didn't agree with Paul Weiss, that is. He didn't agree with him that the silicon aluminum was a semiconductor. And so Paul would get up there and he'd fix some formulas on the blackboard and trying to explain his point of view, and Gray would come up with the ratio. He'd race it off, and this is my view. And it went back and forth at least 4 or 5 times. It was quite a spectacle, and to everybody's amusement, really. But they were two good arguers, anyhow. They put their points across, but they were equally adept in wiping each other's points out. So it was quite a show.
Well, now another one at the Gordon Conference was Hugh Taylor and Halsey.
Oh yeah, that's a famous story. It was people who went to the Gordon Conference back in the 50s, early 50s. See, Halsey was a student. What was Halsey's first name?
George.
George. Oh, how could I forget? George Halsey. He was quite a character. He was a hillbilly from, like I am, from down in North Carolina, as I remember. And he wrote a letter to Sir Hugh Taylor. The story goes that how much he enjoyed the works of J. Willard Gibbs. And he was a guy from a small college. I've forgotten what the college it was, but and he wrote Taylor this letter with an application to get into Princeton. He wanted a fellowship or a scholarship, and I heard Taylor tell this story. He said, "Well, anybody that can enjoy the works of J. Willard Gibbs deserves to come to Princeton." I got him in. And George went to Princeton and got his degree under Sir Hugh. I guess he made it so tough for Halsey, though, that Halsey didn't like Sir Hugh. It was his characteristics of many students and professors, I think, as I found out later. That doesn't apply to me and Paul Emmett, but anyhow, they were both at the Gordon Conference in the early 50s. I can't remember the exact date. It was about the time I was chairman of the conference, about 52. I think it was the year before, the year after. And Halsey, he wanted to play a trick. He was a great imitator, anyhow. He entertained people at the snack bar, people who go to the conference know what I mean. And Halsey was a perfect mimic of Sir Hugh Taylor. It was really comical, but anyhow, I think he was trying to get back at Hugh. That particular night, George went up to Sir Hugh's dormitory room and knocked on the door, said, "Sir Hugh, there's a telephone call for you down in the lobby, telephone booth." So Sir Hugh put on his robe and trotted down to the telephone booth, and Halsey right after him. He went into the booth, answered the phone, and Halsey locked the door to the booth. and Sir Hugh was trapped. He couldn't get out. I don't know who let him out, but after some time, several hours as I understood, Sir Hugh got somebody's attention to get him out of the booth. And he was so furious about this that he went to the management and to get Halsey barred from the conference, and he did. George Hawley never appeared again at that conference in all the years I went to it after that. So that was the story there.
Now, what was it that made Emmett so unique in your viewpoint?
Well, that is a difficult question, but I would say his tremendous memory. Paul Emmett could quote you references for many years back, the exact volume of the journal and the page number almost. He had a tremendous memory for things that had been done in the past, had been published. And I think that's what made him such a wonderful research man. He didn't get involved in reinventing the wheel, in other words. He stayed right on the frontiers of things, and because he knew what had been done in the past. That I think impressed me more than anything else was his ability to cite prior work. Not to say that one of his greatest characteristics, of course, was a human being. Paul was a gentleman of the first water, and I admired him as a human being, first of all, and I think all of his friends will bear me up on that. And I'm sure that many of the people who didn't work with him, like my wife, for example, were very much, really loved the man as a human being. So I think that is the answer to your question, really. As well as his president, President Woodham, who happens to be, as everybody knows, Linus Pauling's sister. And you know, the Paulings and Emmett originated in the same area in Oregon, and they knew each other as young people. I guess maybe in high school. I don't recall whether they went back that far or not. But Paul and Linus Pauling were classmates, of course, at not only at Caltech in their later years, but at Oregon State, or what was the predecessor of Oregon State. And Paul knew the sisters of Linus Pauling, and years later, when Paul was widowed, and Pauline Pauling, I've forgotten her. She had been married. She lost 2 husbands, I think. Maybe you remember, Frank. But anyhow, they got together in later years and as man and wife. And they were very happy the past. I think they were about 10 years they did before Paul's death. They were married about well, when we went to London to the Catalysis Congress in London in 1976, was it? I haven't said 1976. They had just been married at that time. And so we were closely associated with them socially, as well as professionally. Paul was a consultant at Unical for a number of years, and we always had him to come out to our house in Yorba Linda for dinner. There was a standing invitation, and he enjoyed coming out, playing with our dog. We had a beautiful dog. His name was Cedric. He was wonderful. Well, those are some very fun memories that we had, Paul. That's about it, I think. This is many years ago, about I guess in the late 40s. Actually, Emmett Reed had been a consultant for Mole for many years before that, and because he was from Hopkins, and the director of the laboratory was from Hopkins, and his boss was from Hopkins, so actually they liked to have a Hopkins consultant. But Emmett Reed, of course, many people don't know this, but I think if you read the literature, Emmett Reed was quite a pioneer in catalysis also. He was the first one, I think, to translate Sabatier's book. Then he and Paul Emmett together rewrote it and brought it up to date. But anyhow, he was interested in catalysis, and he'd come out to my office, which was way out in the back lot, you know, in those days, at the Paulsboro Laboratory, and he'd always say the same thing. Well, Roland, he says, what's new in catalysis? And I would sit down with him and we'd talk about what's going on. And poor old Professor Reed was, at that time he was up in his 80s. I guess it was my monotone voice, I don't know what happened. But I looked up and he'd be sound asleep. Well, I would say something pretty loud and he'd wake up. And he was an interesting old gentleman, he really was. You know, he lived to be 101, I think it was, and he was still active, and not in catalysis so much as he was in sulfur chemistry. That's where his forte was, in the chemistry of sulfur compounds. But that's the only story I can remember. He, Emmett Reed, he was interested in catalysis, but the subject must have bored him coming from me. I don't know what happened. Anyhow, he would go to sleep once in a while. But we always enjoyed our visits. I don't know that anything specific that came out of him, but he was an inspiration, really. I liked Dr. Reed. He was quite a gentleman. Bring it back on the streetcar, people would look at me, what's that? You know, fueling, you know, how dry ice does. And I think that if it had been today, they thought I'd had a bomb. Oh, sure. But it was nothing. And I'd lug the thing back down to the laboratory. It was, the laboratory, Corcoran Hall, was only about a block. Maybe it was 2 blocks, 2.5 blocks, just off Pennsylvania Avenue. At 21st Street. And but I did a lot of that sort of thing. I do things myself. They didn't have anybody to help me with my glass blowing, for example. So today most universities have a glass blower. But I did all my own glass blowing, and I made a little money on the side by fixing apparatus for the organickers. You know, they'd break an arm off of a flask or something like that, and they'd bring it to me to fix. Oh, charge them a quarter for it, something like that. But you know, that was a lot of money. You know, because my fellowship only paid me $60 a month. And I was like, I live in Washington, $60 a month.
Well, now, Miss Love, what was her position?
Well, she was sort of a laboratory assistant. She was really more assistant to Steve Bernard, as I remember. She worked in the laboratory. She was, I can picture her today. She was she was a lovely person, but she was a very homely woman. You know, the ones you never look at twice. But she was very capable. She was very capable. I don't mean to demean her in any way, because she was a very fine person. And of course, she stayed with Bernard, I guess, until she retired. Bernard stayed on at the Fixed Nitrogen Laboratories after Emmett went to Hopkins. I don't remember how many years, but he took over Emmett's lectureship at the university. I know that. But I don't know how many years, because I didn't see Steve till many years later. I saw him at the PCS meeting in San Francisco. And he remembered me. We had a nice conversation. I always had a high regard for Steve Bernhardt. He was an excellent experimentalist and a good theoretician. But he brought in Teller, you know, as a mathematician to help him out on the BET theory. And I don't know whether he knew Teller before he came to this country or not, but they were both Hungarians, as you know. And he was responsible for. Well, Teller is another story too, really. I should really reminisce a little bit. Teller came to George Washington in the physics department the year I went there, in 1935. And he was very much interested in chemistry too. And he came to all our chemistry seminars. And he was a young fellow at that time. He was in his early 30s. And the story goes that he came to this country pretty destitute and didn't have any clothes and so on. And somebody in the physics department, I don't know whether it was Gamow, who was also there. Gamow was a very famous physicist that was in the department at that time. They took him down to some kind of a clothing store in Washington. I guess it must have been a pretty cheap place. And they bought him a suit of clothes. And he put the clothes on in the store because his other clothes were not very presentable. This is a story. And they walked back from downtown Washington toward the university, and a thunderstorm came up, and Teller got soaking wet, and his pants started to shrink, come up his legs. And they said he was quite a sight when he got back to the campus. Now that's the story they tell. But Teller was quite a character, really. That's before he became famous, of course. He came to our seminars, and he knew a lot of chemistry, believe you me. He was very critical. Somebody among the graduate students, we had a meeting every Wednesday night, I think it was, and somebody was picked to give a discussion of something. I remember I gave a talk on dipole moments, and I didn't know a tadpole. Anyhow, I boned up on it, and I gave a lecture on dipole moments. And Teller was there, and I don't remember exactly what but he made comments and additions and subtractions and criticism and what have you. He knew his subject. He really did. And
did he always have a club foot?
he always had a club foot, yes. But he doesn't speak English today any better than he did then.
Did you ever take a course from him?
I never took a course from him. I'm sorry I didn't. He gave a course. As I understood it, it was a course in quantum mechanics for the layman. And I have heard people comment on that course, how enjoyable it was. People who didn't have any background in the subject at all. And they could understand the man. And that's the mark of a great man. If he can put his subject across to somebody who doesn't know a thing about it.
This is hard to understand.
Well, he did it in such a way that he made things look simple. And that's the mark of a great teacher, I think. I'm very sorry I didn't take the course. I had my hands full, really. I was taking everything they had in the chemistry department. Because I was a little deficient at D&E. I didn't have everything that I should have had. So I had to make up some of it, and particularly in thermodynamics. So I took Gibson's course. Ralph Gibson was one of the great men they had there too. He was at the geophysical laboratory. He wasn't the head of it, but he was head of one department. And he gave a course in thermodynamics, and it was Gibbs thermodynamics, really. And he was a strict teacher. And I remember we had a quiz or something, an oral quiz, and he had me up on the podium, and he asked me this question. I said, I never heard of that. He said, well, all I can say, you ain't been no place and you ain't heard nothing. That embarrassed me, of course. But Gibson was really a fine teacher. Somebody said, I think it was John Kincaid, who was a roommate of mine. He said, yea, Gibbs, the only true God of thermodynamics, and Gibson is his prophet. But Gibson gave a fine course. Then the first semester was thermodynamics, and the second semester was statistical mechanics. And that's where I had nothing as an undergraduate. I had a little thermodynamics. And the Kepler Daniels book, in my day, Kepler Daniels was the Bible of physical chemists. I'm sure that's not true today. But their treatment of thermodynamics was quite different from Gibson's, or Gibbs, however you want to refer to, but it was more practical. That's one thing that Kepler and Daniels did. They adopted, what's his name at Berkeley?
Lewis?
Lewis, yes. Lewis and Randall. And Kepler and Daniels adopted the same approach, and it was more practical, even though it was not precise. And that's the way you've got to look at it today. You can't, we don't have enough data to apply strict Gibson thermodynamics. You have to make some approximations here and there. Things have changed quite a bit, of course, since I was in school. There are a lot more thermodynamic data available, which weren't available in those days. Anyhow, that's the story of Teller. My brief association with him, this goes back now, how many years? 1935 is 54 years. That's a long time. And look where he's got in 54 years.
What was George Washington University like in 1935? Small?
It wasn't too small. They had the undergraduate classes were, I can't really remember too much, but I was an instructor in physical chemistry lab, and I had about, I would say 20 people in the laboratory class. I learned more physical chemistry doing that than I did in class, I'll tell you. It was, they had a graduate student body, mostly made up of government employees. The Department of Agriculture, for example.
Have a good night.
You too.
Thank you.
You again.
The Department of Agriculture and Bureau of Standards supplied a lot of night students. In fact, at the time I went there, hardly any courses in the graduate school were taught in the daytime. Always at night, to take advantage of the students that are available from government employment. But they had a reasonably good student body. They had the lecturers, the professors, were specialists in the government service mostly. I remember I took a course from Amber, who was in the Department of Agriculture, on sugar chemistry. He was an expert in sugar chemistry. And of course Gibson was at the Geophysical Laboratory, which is really not a government laboratory. It's a Carnegie Foundation laboratory. And Emmett, of course, was Department of Agriculture, or Fixed Nitrogen Laboratory. But the regular staff, there were no outstanding people in the regular staff, I would say. There were good people, but not outstanding. The most outstanding one would be, I think, Charles Mazer, who is now retired, and he's the only one left.
Wasn't he the one you called?
I talked to him several years ago. I was no worse than he is. But it was a good school, relatively. Today, I don't think it's as good as it was then, though, from what I understand. I haven't been back for years. They had a good head of the department, Mill Street. Can't remember his name. It's strange. He's dead. He's been dead for quite a few years. But he was a good man. He was a good organizer. Van Evera, Benjamin Douglas Van Evera. He was from Iowa. He was a graduate from Iowa. He was a good man. But they had, as I said, they had no men on the regular staff as outstanding as Emmett and Gibson, Ambler, and there were several others. I don't recall their names now. I took almost all the courses they had to offer in the graduate school. It took me 2 years to get through my master's. They were pretty strict, actually. I was impressed. A lot of places you can get your master's in 1 year, but you couldn't get it there in 1 year unless you really had outstanding background. I knew one fellow that did. Got it in 1 year. But it was a rather enjoyable school because we had so many facilities at our fingertips. For example, the Library of Congress. I spent hours and hours in the Library of Congress. In those days, they allowed me to go back into the stacks in the scientific section, particularly. And I had more fun looking up really ancient publications they had there, way back in the early 1800s. I did it sort of as a hobby, in addition to my own literature research. I had to do a lot of research on the reaction of ethylene and hydrogen, which goes way back to Savati's time, or about that time now. But I enjoyed the privilege of going into the Library of Congress and spending the hours I did. Today, I'm sure you couldn't. You have to know what you wanted and they'd get it for you. But in those days, Washington was a pretty lax place in a sense. You could go into Congress, you could watch the Congressman section. Nobody paid any attention to you. You could even walk into the White House. You couldn't get upstairs, but you could walk into the White House. And, that was long before there was any fear of terrorism or assassination, things like that. Although I'm sure a lot of people probably thought about the respect for Roosevelt. That was in Roosevelt's second term. I voted for him from the hospital bed. I remember in 1936, I suddenly came down with a attack of appendicitis, and I didn't want to go to the hospital. I said, "Well, I'm all right." But I got sicker and sicker, and so the stockroom clerk at the university took me over to the hospital, and the doctor examined me and says, "You've got to have an operation right away." I said, "No way." He says, "Okay, it's your funeral." And I'm beginning to think about that. And so I said, "Okay." But it was, you know, the amazing thing about that experience was the cost relative to today. First of all, as a student at the university, I was covered for the hospital bill. But all I was responsible for was the surgeon. And his fee was $100. It took me a year or so to pay it off because I didn't have enough money. But he said, "Take your time." He accepted $10 our payment. I paid it off. Oh, today, it's amazing. But I was on about a 20-bed ward, I guess it was, at the University Hospital. And I was a pretty sick boy. And I guess they thought I was sicker than I thought I was, too. I remember my aunt was summoned. She came up from Huntington, West Virginia. So she and my cousin, to supervise my last rites, I guess. Because they thought I had developed peritonitis. And I had a high fever, you know, and to make things even more uncomfortable for me, the nurse said, "You know what happened to the last patient in this bed? He died of peritonitis." Well, anyhow, it turned out to be different. There was a bladder infection. I recovered, obviously.
Fortunately.
But those were tough days in a way, but I look back on with a lot of good memories. So, particularly getting along on $65 a month, worse than going, having my lunch in the
Little problem with
Quickies
that.
drugstore. Well, I wasn't the only one. There were three of us, three Sanders fellows, so-called. The Sanders family had established its fellowships several years before. And of course, to them, an income of $60 a month was quite substantial. If they had to endow it, I don't know how much the money's in the endowment, but probably not by today's standard, but not very much. But anyhow, they turned out quite a few Sanders fellows who went on and made a fair success out of their lives. I knew several of them. I have a good friend from Southern California. We have lunch every 3 weeks,
Yeah.
3 months. He was one of the Sanders fellows in my last year there. He went on to, he got his degree, his PhD at Illinois. I think he worked here under Hopkins in Illinois. Rare earth chemistry. Anyhow, this